And in the last class, we discussed about the derivation of the relation between let me maybe I should open the whiteboard. So we discussed about the relation between shear stress and pressure drop and the volume flow rate in a fully developed steady laminar flow through pipes. And if you remember the last slide we covered, that was this slide on which we discussed that the velocity and volume flow rate are function of D4. They are directly proportional to the force power of diameter, and then it is inversely proportional to the viscosity, and it is also inversely proportional to the pipe length. Okay, so as we discussed the relation uh, between, if I can write it here, just a minute. So let me open a new one. So in the last class, we discussed the relation of delta P, tau, tau omega, and Q, which is the volume flow rate for fully developed laminar steady pipe flow. Now, as we know that what is the function of tau W, which is the wall shear stress, it usually produces drag force which resists the flow of the fluid flow through pipe. Through pipe. Now, okay, that is good that we know that omega is mu into du upon dr, and r is equal to r. But it would be far more convenient if we can represent this delta V in terms of some friction factor. So it would be better that if we can represent this wall shear stress relation with delta V in terms of friction factor. So we can determine that relation of delta V with the friction factor. So friction factor we represent it with symbol small f. So here we can determine it by the non-dimensionalization of this pressure drop. So this delta V is the pressure drop between, if I can draw a small figure here. So delta V is the pressure drop between entrance and exit of the pipe. So the pressure which has been dropped due to this wall shear stress, that is delta V, right? So here I think. Okay, so we'll just leave it. So we are talking about relationship of delta P with the friction factor. So let me uh, non-dimensionalize delta P. So for the determination of delta P in terms of friction factor, what we do that we write non-dimensionalized delta P with respect to uh, so we can non-dimensionalize delta V by dividing it with half rho v square. So we can easily see that the dimension of delta V are Newton per meter square, and also the dimension of this in the denominator, that is also Newton per meter square. So now, as we discussed in the last class, that delta P can be written in form of the mean velocity by this relation, which is delta V is equal to 32 mu L V upon G square. If we see this second relation here, which is this one, V is equal to delta V D square upon 32 mu L, right? So from here we can write delta V, that is equal to 32 mu L into velocity. This V is the mean velocity and divided by D square. So let's put that value here. So if we put that value here, So that would be equal to 32 mu L V. V is the mean velocity divided by d square divided by half rho v square. Now we can write it in a little bit rearranged form. So we can write it 64. Now we can see mu v. So here we can here v would be cancelled with this v. So we can write it mu upon rho v d. So there is d square. So we have only written d here. And then it means that we have got length here, so L upon D, that is also a non-dimensional term. We also know that this term, what is this term? This is 1 upon Reynolds number for pipe, because Reynolds number for pipe is rho Vd upon mu. Yes, anything? So it was 1 upon Reynolds number, and then the L upon D is also a non-dimensional number. So now you can see that we have non-dimensionalized delta V in terms of velocity, and then this can be written like, let me scroll it a little bit, and it can be written in terms of, we can write it 64 upon Reynolds number L upon D, and this is equal to delta P, that is half rho V. So here this quantity we define it as friction factor F. So basically, for the laminar fully developed pipe flow, it is the inverse of it is inversely proportional to Reynolds number. So it means that we can write it like this. In the next step, we can say that delta P is equal to F L upon D half rho V square. So if we plot it, this friction factor with Reynolds number, if Reynolds number is increasing this way, so because it is inversely proportional, from here we can see that F is equal to 64 upon Reynolds number. So it means that it would have some kind of this inverse linear relation. But don't you think that it is surprising that if we increase the Reynolds number, so the friction factor is decreasing. So if we think about physical flow, so whether it shouldn't be the case that if we increase the velocity of the flow, then the frictional force or the drag force should increase rather than it should decrease. So the answer for this lies in this quantity, because if you see that here it is v square, and in this because when we say that delta v is fl upon d into half rho v square, and f has got 64 upon Reynolds number, so Reynolds number has something we have got, we can say that if we replace it with that quantity, just a minute, let me write it on the next point, just for the clarification. And so I am writing it again in terms of 64 into rho vd mu and L upon D into half rho V. Now you see that we can cancel V with the just V square. So delta P is basically directly proportional to velocity. So that is that we expect that if we increase the velocity, then the pressure drop would increase, then the drag force would increase. But due to this half rho v square, the friction factor, because we have defined it like 64 upon Reynolds number, so it gives us the misleading what do you call it? That misleading idea that maybe friction decreases as we increase the Reynolds number, but actually it increases with the with linearly with the velocity. So that is what we really expect. So please don't think that friction decreases as we increase the Reynolds number. Right. So that was it. For now, we can go through the slides, and then we can do one numerical problem for friction factor and these forces calculation for laminar flow, and then first of all we discussed about the concept of friction factor with respect to non-dimensionalization of delta p. So delta p, we replace it with the mean velocity by the relation which we derived in the last class, and then from there we can kind of write it where f is the we call it friction factor, and also we call it Darcy's friction factor because that is the name of the scientist which proposed this. And if we plot it, we can see that we have got a inverse linear relation between friction factor and dynamic. But the total drag force increases directly with the velocity, as I explained it on the whiteboard. Now, now we can do a very small numerical problem to demonstrate that how different things are calculated for study a laminar pipe flow. So the volume flow rate of a fluid whose viscosity is given, viscosity and S is given in a horizontal pipe is to be monitored by measuring the pressure difference between point 1 and point 2. So point 1 and point 2 they are here, and determine the wall shear stress and the pressure drop delta P for if the volume flow rate through that pipe is zero point 0.5 feet cube per second. So if we are given the volume flow rate through this pipe, and we are also given the length between that pressure gauges from which we calculate delta P, that is 6 feet if you see in the figure. So we need to calculate that how much pressure drop would be occurring between 1 and 2 for a volume flow rate of 0.5 feet cube per second and the wall shear stress, right? So for the calculation of delta V in terms of Q, if we just a minute, if I can, because delta P and Q relation we have derived here. We can see that delta P and Q relation is given in the last relation. Delta P is equal to 128 mu L Q divided by pi d raised to power 4. So first of all, we calculate delta P from here. So delta P would be equal to from here we can calculate. Let me do it here. So delta P, if I write it again here, that is 128 mu L Q upon pi d raised to power 4. And then if we put the values, we have been given the value of mu, which is 3.8 into 10 to the power minus, let me see it from here, 128, it is, what is that, 3.8 into 10 to the power minus 3. So 128 into 3.8 into 10 to the power minus 3. Okay, one thing I need to mention here, that because it is in feet square, so we need to make sure that everything is in feet square. Like the diameter of the pipe is given 3 inch, so we need to convert it into feet if we are going to have the same feet unit for the mu. So here 123.8 into 10 to the power minus 3, length is 6 feet. So we write it 6 feet, and then Q value is 0.5 feet cube per second divided by pi into and diameter is 3 inches, so it should be a 3 by 12 to make it in feet. And then if we calculate delta P from here, so delta P is comes out to be 120, 119, I think. Yes, 119. If I remember it correctly, it would be 119 pound per feet, right? So then the second thing we need to calculate, that is tau omega. So for the tau omega in terms of delta P, if we see the lecture slide which we did the derivation on in the last class, so delta P in terms of tau omega, if we go back, so delta P in terms of that tau omega, that is written here. Delta P is equal to 4L tau omega upon d. So let me write it here. So delta P is equal to 12 tau omega 4L tau omega upon d. So now, but the thing is, the a word of caution here, that this relation is only valid for laminar flow. So it means that first of all we need to determine that whether this pipe flow is laminar or turbulent. If this is a laminar pipe flow, only then we can apply this relation. So let me do that. Uh, because for that calculation, so if we first of all calculate for the how to calculate that the flow is laminar or turbulent, we need to calculate Reynolds number, which is rho Vd upon mu. If it is less than 2300 or 2000, let's suppose, then we can say that it is laminar flow. So for the calculation of Reynolds number, we know the density, we know the diameter of the pipe, we know the viscosity, but we don't know the mean velocity. So mean velocity can be determined from the volume flow rate, which is V equal to Q upon A. Q is given 0.5 feet cube per second, and then feet cube per second, and then area we know that it is pi by 4 d square. So d square here would be 3 by 12 square. From here, if we calculate the velocity, it comes out to be 10.2 feet per second. Right. So now the second thing we need to calculate, that is Reynolds number. So if we put in the value, low value is let me go back to that slide. So low value here is 2.05 slugs per feet cube. So 2.05, then we have been given velocity, we have just calculated diameter is 3 by 12, mu value is 3.8 into 10 to the power minus 3. If we put in the values, Reynolds number comes out to be 13, it is approximately 1380. So 1380, that is of course less than 2000, so it means that the flow is laminar. So for this, now we can use this relation. So from here, tau omega would be equal to delta P into D divided by 4. So from here, delta P we have calculated 119 in part 1, diameter is 3 by 12, 4 into 6, 6 is the length of 6 feet is the length of the pipe across which delta P is 119. So from here we can calculate what shear stress, that comes out to be 1.24 pound per feet square. Right. So this was part A for this numerical problem. Part B is the where we need to calculate the net pressure force. So net pressure force, if you see this pipe flow, net pressure force would be acting in the positive x direction, and the net shear force, which is being applied by the pipe surface, that would be acting in the negative x direction, so that they are balancing each other. So there is no acceleration of fluid. So the flow is fully developed. It means that velocity does not change in x direction. So it means that if we calculate these two forces, net pressure force and net shear force, they should be equal and opposite if it is fully developed laminar steady pipe. So pressure force, we know that that pressure force calculation, we can represent it by using F of P, and Fp would be equal to delta P into, no, delta P is Newton per meter square, so we need to multiply it with some area. So area would be the cross sectional area of the pipe, because that pressure force is acting on the fluid. So that is flowing through that cross section. So that cross section is pi by 4 d square. So if we put in the values, so that comes out to be, we know delta P 119, or I think it was 119. So d square is 3 by 12 square, and then if we put in the values, it comes out to be 3.84 pound force. And then similarly, we can calculate shear force. So now for the shear force, if we see again, it has the unit of pound force per feet square. So it means that it also needs to be multiplied with some area. But now we recognize that wall shear stress acts on the pipe surface. So pipe surface, if we want to calculate the pipe surface of a particular length, we know that that would be equal to circumference into that length. So that would be pi dl. So tau omega into pi dl. So it should be small. So diameter is given, length is given, tau omega we have just calculated 1.24. So if we put in the values, it comes again equal to 8 foot on 4. So it means that both forces are kind of equal. So we can say that it is steady, laminar, fully developed pipe flow. So there is no acceleration because the driving force is equal to the resisting force. So there wouldn't be any net force on the fluid element. So the flow would occur with a constant velocity along a straight line. So that was it. So up till here we have discussed about the laminar pipe flow. So, but unfortunately, in practical engineering applications, all the flows or majority of the flows they usually tend to be turbulent flow. So it means that all the things we have done that is only applicable to laminar pipe flow, which is flowing steadily in a fully developed form. So now we need to consider the contribution of turbulence in that laminar flow, right? Because most of the cases they are usually having some kind of turbulence in the pipe flow because the Reynolds number is usually more than 4,000 or so they are kind of turbulent flow. So let's suppose that we have got a pipe in which the flow is happening in a horizontal pipe. So if we increase the Reynolds number, so how can we increase the Reynolds number or the volume flow rate of the flow? That is very simple. If we open the valve, and so it means that the flow would increase, the flow velocity would increase. If the flow velocity would increase, then the volume flow rate would increase, and consequently, the Reynolds number would also increase. So here, the if we see this graph, here we have got on the x-axis we have been given that this is the volume flow rate, and then no, on the x-axis it is time, and on the y-axis we have been given the volume flow rate. So now it is a kind of velocity at a point. So you can see that whenever the Reynolds number is less than 2000, that velocity signal is very smooth. That velocity is increasing with time because we are opening the valve, but it is kind of very smooth line in this portion. But when the Reynolds number becomes greater than 2000, so between 2000 and 4000, we can see some little spikes. Let me zoom it a little bit, maybe it would be more easily visible in this. So here you can see that we have time on the x-axis and the velocity on the y-axis. So we can have some gauge to calculate velocity at certain point, and we can see that there are some fluctuations, intermittent fluctuations in the transitional range. And if we keep on increasing the volume flow rate by opening the valve more and more, then we can see that turbulent portions are there, right? So that is something which we usually experience when we open the valve uh, in our sink. So now laminar to turbulent transition occurs as the Reynolds number exceeds its critical value, which is 2000 in the pipe flow. So that can be visually seen as the top figure is for the laminar flow. As we increase it, you can see that there is some kind of transition, and then there is kind of some turbulent vortices in the pipe flow, which can be visualized by using high-speed cameras or by injecting some dyes, dye in the color dye in the pipe. So now, what is the contribution of pipe flow, or what are the major characteristics of this? What do you call it? Turbulent flow. What kind of impact it would have on the flow? So let's uh, discuss it on the whiteboard. So turbulent turbulent flows turbulent flows, they are characterized by random motion. We also call it chaotic motion. And then second thing, which is the characteristic of turbulent flow, that is rapid mixing. mixing of the fluid. Okay, why there is a rapid mixing? Because in the turbulent flows, we have kind of eddies, vortices. We also call them eddy, or we call it vortex. 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 So, because of the vortex, what happens that if the fluid particle is near the wall, it would have very low velocity. But due to that vortex takes that fluid and takes it into the center line portion where the velocity is very high. So it means it is kind of increasing the mixing of fluid, and you can okay now. Third thing, which is the consequence of this, is the fluctuations in flow. Fluctuations mean that velocity and pressure, fluctuation. How they are fluctuating, because in the turbulent flow, because that is a kind of chaotic motion, so it is quite possible that in a same streamline, one fluid particle is having a very low velocity and the other fluid particle is having a very high velocity, because there would be chance that there would be some vortex in this direction. So what it would do is that it would take a very high velocity fluid from the center line to the near wall region where the velocity is low. So that's why it would have more velocity. The fluid particle which has been transported from the center line to the pipe near wall region. And if we want to show that turbulent velocity signal in time. So this is time. This is some. It is kind of u velocity. So we do stream velocity. So it can be something like this, right? So it is kind of showing us the kind of, because it has got one mean value. Mean value means that it would give us an average value of this. Okay. So we call it. We can say that an instantaneous velocity has two components. One is the mean value and one is the fluctuating component. So this is, let me write it. This is instantaneous velocity. Instantaneous, instantaneous velocity. This is mean velocity. Now we are this mean velocity, that is in time. We are talking about mean velocity in time, not in the space. We are talking about mean velocity in time, and this is velocity, right? So this is so I can also show this on the practice, right? So it has got three characteristics. Okay, last thing which I forgot to mention, that is higher drag shear force. So that is also the result of these eddies. So you can see that normally the velocity in the near wall region, that is very low, but if one vortex take a very high velocity fluid near the wall, what will happen that du upon dy, because we know that tau of omega is equal to mu into du dy, and r is equal to r. R is equal to r is the pipe surface. So because if the velocity in the near wall region will be increased due to transport of high velocity fluid in the near wall region, so that's why the drag force on that surface would be more. It means that the shear stress would be more. So it means that what is the consequence of this? That it means that if the aeroplane, if it is having some cruise velocity, so at that velocity the flow would be turbulent. So it means that it would have very high shear stress. So it means that the fuel consumption would be very high as compared to if it were to travel in a laminar flow. But because for the cruise speed, because we want to have some kind of lift and force for the aeroplane, so it means that it has to travel with some cruise speed, and unfortunately at that speed it is turbulent flow. So that's why fuel consumption is high. So that is an active area of research, that how we can locally make it laminar flow near the aeroplane surface, so that the fuel consumption can be reduced. So these are the three characteristics of turbulent flows. the mean velocity component I have told you, and I have also told you that the instantaneous velocity can be decomposed into two components. One is mean velocity and one is fluctuation. Now, mean velocity can be calculated between two time instants, between t naught and t naught plus t, by integrating it with time and then divide this integrand by the total time of the integration, which is t in this case. So one characteristic of this u prime is that if we take the average of u prime, that would always be equal to 0. That it means that the fluctuation, if we take the average of fluctuation, that should be statistically equal to 0, because fluctuations are usually the difference from the mean value. So it means that half of the fluctuations would be positive and half of the fluctuations would be negative. So if we add them all together, that would be equal to 0. And the same thing can be shown mathematically, that because u prime is u instantaneous minus u mean, so we can do the a little bit of integration here, and we know that u dt upon 1 upon t can be written u mean, and we can easily see that mean of fluctuations or average of fluctuation is always 0. So how can we determine that a particular flow is how much turbulent? So that is quite easy. That we can take the square of fluctuation rather than only the average of fluctuation. We take the square of fluctuation. So it means that when we take the square of fluctuation, the negative fluctuation would also become positive. Here you can see that this gray area where the mouse cursor is, it was in fact negative fluctuation, but because we have taken the square of the fluctuation, that negative fluctuation also comes out to be positive fluctuation, and the positive fluctuation would also be positive because of the square. So now we could have a non-zero value of fluctuation, and usually in the statistics we use a term which is called root mean square. So we take the square root of this average square of fluctuation, that is root mean square. And for the in turbulent flows, we call it turbulent intensity. That we divide the root mean square of fluctuation divided by the mean velocity in time. So that is called turbulent intensity. So why we need these statistics? Because we need to distinguish that at maybe 10,000 how much turbulence is there in the flow. So we can always calculate the turbulent intensity or the root mean square of the fluctuation, and how much there would be turbulence if the Reynolds number is 1 lakh. So we can visualize that turbulence at 1 lakh would be far higher. It means that these values would be far higher for Reynolds number 1 lakh rather than 10,000. So that is just to judge the level of turbulence in a certain flow. Okay. Uh, Another concept which needs to be discussed here, that is shear stress, because we mentioned for the turbulent flows that the shear stress is higher. So now how can, because for the laminar flow, if you remember that for the laminar flow, if we want to calculate shear stress, that would be mu into du upon dr. Right. So uh, what is this shear stress? From where it comes? It is on the microscopic level. Okay, let me give you a physical interpretation of this shear stress. Let's suppose we have got this is Earth surface, and here I have got imaginary surface. We call it some A B. Now we know that usually in pipe flows on the microscopic level there would be some. Here, if I take one point, here the velocity maybe it would be 1 meter per second. Here maybe it would be 3 meter per second, and in the as we go away from the wall, it would be 5 meter per second, 7 meter per second, and so on. Right. Now, if this fluid particle, which is here, if it because they are usually they oscillate at their mean position, and in the gases they also kind of flow. So what if that if it travels in this direction upward, and it reaches at this location where the average velocity is 5 meter per second. So now it finds itself at a place where the average velocity is more, right? So it means that now the fluid particles which are on this layer, which is having 5 meter per second, they have to somehow increase the velocity of this particle so that it can move along this line, right? So it means that there would be some kind of momentum transfer between this low speed fluid and this high speed, right? So in this way, these particles in this line, they would kind of feel some kind of retardation. They would feel some kind of deceleration. Why that? Because when this would travel here, they have to give him some momentum so that it can travel with the 5 meter per second. And similarly, if a particle which is was here and it comes here downwards, now what will happen that in that case it would find itself at a place where the velocity is low. So it means that it has to deaccelerate. So it means that in a way, this layer would get some momentum from the top surface, from the above layer, due to the translation of this particle, right? So in this way, the shear stress, when we say that there is some kind of resistance between the layers, so that resistance comes due to this translation of these particles along a streamline. So it means that it is kind of giving that acceleration and deceleration of particles due to their oscillation. So this is on the microscopic level. But what happens in the turbulent flows? Because in turbulent flows we have got some kind of eddies or vortex we call it. So in turbulent flows, these translation between the layers, they are very much at a higher rate, right? So it means that there would be, if there were only one or two translations in the laminar flow, maybe in turbulent flow there would be 10 to 20. So it means that there would be some contribution from this particle translation due to these vortices. So there would be another vortex that would be kind of taking high speed fluid to the pipe surface. So it means that if we want to show that the contribution of that turbulent flow, then the total case set we can write it as tau is equal to mu into du upon dr minus rho u prime p prime, right? So this is, we call it turbulent case. And there is one thing, that there is a minus sign. Usually for the turbulent flow, there would be microscopic contribution due to viscosity, and the turbulent shear stress contribution due to fluctuation. But there is a minus sign. So it means that this quantity rho u dash b dash, it is always negative. Negative means that if u prime is positive, then b prime would be negative. And if u prime is negative, then b prime is positive. Now, how can we see that in this figure? Let's see that here the velocity was 3 meter per second. Now, because it is moving upward, so v prime would be positive. So we are talking about this. V prime would be positive, right? Because it is moving upward. And then when it goes here, it has got 3 meter per second, the average velocity is 5 meter per second. So fluctuating component of this particle would be negative, because 3 minus 5 is negative 2, right? Minus 2. So in that case, the product of u prime v prime would be negative. So the overall effect would be the addition of shear stress. And secondly, we can consider this case: u prime is greater than 0 and v prime is less than 0. If this fluid particles come down here, where the Morse cursor is, v prime would be negative, because it is going in the negative y direction, and then u prime would be more, because 5 meter per second velocity particle would come in the streamline where the average velocity is 3 meter per second. So the fluctuating component would have a velocity of plus 2 meter per second. So that's why this product of rho u dash u prime v prime would be negative. So I hope that you understand this point. Please, I would again request that if you don't understand anything, you are free to ask question at any point. I am more than happy to repeat any concept which you couldn't understand. So this was the concept of microscopic and macroscopic shear stress. So macroscopic means that due to that macroscopic motion of due to those vortices, and this microscopic is the translation between the layers due to oscillation. So that is you can see here that tau turbulent is minus tau u dash v dash, and I have told you that this product is always negative. So the overall contribution is the addition of that turbulent shear stress, and you can easily see that in the near wall region we call it viscous sublayer. That region is called viscous sublayer. In that region, the laminar portion has greater. If you see here that the laminar portion is greater here, but as we go towards the center of the pipe, then you can see that this dotted line, it tells us about the distinction between laminar and turbulent shear stress. On the left hand side, we have laminar shear stress. On the right hand side, we have turbulent shear stress. So in the at the wall, we can see that all the shear stress is due to laminar shear stress, while that because uh, uh, due to no slip condition, there is no velocity fluctuation at the pipe surface. But as we go away from the pipe, the turbulent shear stress increases rapidly, and the laminar shear stress decreases. And at the pipe center, you can see all the stresses due to turbulent shear stress, and laminar shear stress would have very uh, negligible contribution. So, if there is any question in pipe flow, the losses can occur in two ways. One is the due to the wall shear stress, and the second one is the what you call it the components, as we discussed in the previous week lecture. So. For that we need to compare the energy equation with the Bernoulli equation, because if you remember from your chapter 5 knowledge that, or FM1 knowledge for that sake, that Bernoulli equation gives us the relation between pressure, velocity, and elevation when there is no frictional force. But because in case of viscous pipe flows, because we are saying that there would be some viscosity effect, so it means that there would be some kind of frictional losses when the flow happens through that pipe. So if you haven't read in chapter in FM1 the section 5.33, please do read it, because it gives you the comparison between energy equation with the Bernoulli equation, which would be the basis for the calculation of losses in chapter number 8. So I have put that material in a concise form in the lecture slide. So we are going to discuss it here, so that how we can measure the losses for the due to viscosity by the comparison of energy equation with the Bernoulli equation. So let me show you that here. So first of all, if we know that for an incompressible one-dimensional steady flow, the energy equation can be written m dot into. If you remember that if there is no shaft work, if you remember that, let me write it on here from your thermodynamics knowledge. First law of thermodynamics, that if you remember that Q net in minus W net out is equal to delta E. That is the statement of that is the mathematical form of first law of thermodynamics. Now this delta E, that is basically if delta H, which is enthalpy, plus delta PE plus delta KE. So that is the changes in potential energy and kinetic energy, and delta H, we know that H is equal to U plus PV, P upon rho, right? H is the enthalpy, U is the internal energy, P upon rho is the flow energy, we call it. So that is which we must have learned in thermo 1. So if we know the shaft work, then we can and multiply it with m dot. So this equation can be written in form of this. Here this u is per unit volume. You can see a little bit of tilde here, tilde. So that is, we are talking about per unit volume. Then we have got this u plus p upon rho, that is enthalpy. Then this is the change in kinetic energy, and then gz out minus gz in, that is change in potential energy, right? And that is equal to q dot net in. So because of the frictional losses, there would be some kind of conversion of the frictional energy into thermal energy. So that's why we have kept this term, that W shaft in, that is equal to 0 here. So now if we divide it with the mass flow rate, then and then rearrange it in a form that P out upon rho plus V out V square out upon 2 plus G net out is equal to P in plus V in square plus G net in. So if you see these three terms on the left hand side and the three terms on the right hand side, they also appear in the Bernoulli equation. And then there is an additional term on the right hand side, which is minus U out minus U in minus U net in. So this term is the due to that friction losses, right? So for the clarity, I have written these Bernoulli equation here. So you can see the fourth equation with the second equation, they are essentially the same apart from this subtraction of this term U out minus U in minus Q net in on the last thing. So this term is basically the loss which the flow experiences due to friction, right? So I have written it here again. Now we can clearly see the comparison between the energy equation and the Bernoulli equation. Energy equation is written on top and Bernoulli equation is written on the second, and we can see the additional term which is the frictional loss term on the in the energy equation term. So for the steady incompressible flows without any frictional effect. So that is the major assumption, one of the major assumption in the Bernoulli equation, that is always equal to zero, right? But for the case of steady incompressible flow with friction, so we are talking about viscous flow through pipes. In that case, this is always greater than zero. So that's why we would have some uh, the energy would be at a lower value at the end of the pipe due to those frictional losses. So the energy which is coming in, that would have a little bit less value at the outer stage of pipe due to friction losses, because that part of energy has been converted into thermal energy. So it means that the flow energy would be a part of that flow energy has been converted into thermal energy, which increases the temperature of the that flow maybe with a few degrees or maybe less than few degrees. It depends that how much losses are there. So it is just analogous of this, that in winters we usually rub our palms against each other. So that is the one way of having that conversion of frictional energy into thermal energy. So that concept is also happening on the in the fluids as well due to the interaction of molecules. So there is some conversion of that flow energy into frictional into thermal energy. So this term represents the loss of useful energy that occurs due to friction. So this loss, it means that it is not being destroyed. That energy is being changed into thermal energy. So which means that the flow temperature should increase a little bit. So now we can see that the additional term on the right hand side. So the first six terms, they are the same as it was for the Bernoulli equation, but this loss term, that is due to frictional losses, and the losses due to flow inside the different components like balls, tees, joints, and pumps, turbines. So there are some kind of losses due to those flow discontinuities, right? So most of the turbulent pipe flow analysis is based upon experimental semi-empirical formulas, because we know that, as we discussed in detail in chapter number 6, that the solution of Navier-Stokes equation is only possible for certain simplified cases like flow between parallel plates if the flow is laminar fully developed. But for the turbulent cases, there is no generic solution. So it is rather experimental or semi-empirical correlation which are available for the turbulent pipe flow. So it means that we need to come up with those patterns, so which we would come across in the next few slides. So here the energy equation is again written. Now the short work is written here in addition, right? Because for the fluid flow problems in the piping system, we usually have pump or turbine installed. So that's why we have put W shaft net in. So in case of pipe work, pump work, we would have W shaft net in would be a positive. Otherwise, if we are talking about pipe application, there is a turbine installed, then there would be W shaft net in negative. And the second consequence of this, due to friction, as you have discussed in case of thermodynamics, that the actual pump work is more when there is a friction involved. That is represented by isentropic efficiencies. If you remember the TS diagram for the steam power cycle or gas power cycle, so the concept of pump isentropic efficiency and turbine isentropic efficiency, they include the frictional effects. So the consequence of including the friction for the pump is that the pump work required is more, and the turbine work which we get out of that system, that is usually less. So this is we have written it in terms of loss, and then the loss term can be divided by comparison with the Bernoulli equation, which we have done on the previous slide, and then more input work is required in case of pump, and less output work is required for the turbine. If I show you the TS diagram for the if you remember your thermo two course, I am very hopeful that you have taken a course of thermodynamics too, maybe. In your previous chapter, in your previous semester. So in that, if we draw the TF diagram for that, so if you remember that there is a bell-shaped curve here, that is the saturation curve, and then there is kind of, if we draw the cycle here, that is like this. That is pump work, then we have got boiler here, and then superheated region, and then that is turbine work, and then this is something. So this is ideal when there is no friction. But then when there is friction, then I can draw it here. Then due to friction, that is increase in pump work, and then from here, then we would have some reduction in turbine work. So the pump work, this is let me write it. This is pump work. Pump work, here you can see that for the dotted line or the red line, it has been increased by an amount, and then the turbine work that has been reduced. Right, so that is the concept which is being written in the last bullet point here, right? And then we can write it. This is the when we divide this with the gravity, we can always write the Bernoulli equation or this equation in terms of head, right? P upon gamma plus B scaled upon 2g plus z out. So we are talking about in head form. So this is the pressure head, velocity head, and then this is the elevation head, and then HS is the shaft work head, and then HL is the loss head. So HS can be written W dot shaft net in divided by mg. So that can be written in case of gamma q. Gamma we all know that is rho g, and rho into q is the mass flow rate. So rho g is gamma, and q is the volume flow rate, and that is the shaft head, and then the total head loss in a viscous flow through pipes is divided in two parts, as we discussed in the introductory lecture for this chapter, that it has got two parts. One is the major loss, which is due to friction. Frictional losses are the wall shear stress losses, and HL minor is the loss due to installation of different components like walls, teeth joints, and then pumps, turbines. So all these losses due to discontinuity in pipe flow, that comes under HL minor. But the word which but the concept which needs to be clear here, that major doesn't mean that always this frictional losses would be more than the minor losses. But we just categorize it like this, that the friction losses there can be written like major losses, and the minor losses are due to the flow discontinuity in those components. So this has nothing to do with the magnitude of loss. So major loss is due to the viscous effect in statewise, and the minor losses that had losses in various pipe components, elbows, teeth, walls, etc. So now we are going to discuss that. I think we have got uh, what is the. I think we can quickly cover the uh, the loss in terms of major loss in terms of friction factor, right? So if we discuss take a pressure drop in viscous pipe, so having a surface roughness, now we have also included the surface roughness in the analysis, right? Delta P is the function of mean velocity, diameter, length, and surface roughness, which is epsilon, then the fluid properties, which is mu and rho. So if we use a method of repeating variables or the method by inspection, we can determine the non-dimensional pi term for this by using dimensional analysis, which we done in chapter number 7. So in that case, if we do because we have got 1, 2, 3, 4, 5, 6, 7 parameters, so 7 minus 3, that would be the 4-dimensional pi term. So delta p upon half rho v squared is a function of rho v d upon mu L upon d and epsilon upon d. Epsilon upon d, it represents the relative roughness of the pipe. It means that the ratio of the roughness element, which is at the pipe, divided by the diameter of the pipe. And L upon D is the ratio of length of the pipe and diameter of the pipe. And the experience shows that this is always directly proportional to this delta P. So we can take it out of this functional form because they are usually directly proportional. So we have taken L upon D out of this functionality, and now we can make use of delta P upon half rho V square in terms of friction factor. We know that delta P upon half rho V square is equal to Fl upon D, which we have covered here. If I go back here, delta P upon half rho V square is equal to Fl upon D. From there, F would be equal to delta P upon 2 into delta P upon rho V square into D upon L, which is written here. uh, Here if I show you, so F is equal to this, uh, F is equal to delta P D upon L upon half rho v square. Let me maybe, if we put this value here instead of delta V, if we want to put this value F upon D upon L into rho v square upon 2, so eventually we can come up with friction factor is a function of Reynolds number and epsilon upon D. Okay, can you please confirm that you have got any class now, so that I can show you the derivation on the whiteboard, or you have got the class at 2:50? G. Hassan Mustafa or Hashir, is there a class at 2:50? Can I take 5 minutes?
Yes, आप लेने चलेंगे.
Okay, thank you very much. So let me take the snapshot here. Just a minute. Just a minute. So let me take it on the whiteboard, and then from there we can do the. Okay. So here I wouldn't take much longer. So let me. Okay. Now from the second relation, we can show that delta p delta p delta p is equal to f f into rho v square upon 2 divided by d upon f, right? So if we put it here, somewhere here, then we can, if we write it here, f into rho v square upon 2 divided by d upon l, and here we have got half rho v square, which is this one, is equal to l upon d, function of Reynolds number and epsilon upon d. So now you can see that this rho v square upon 2 would be cancelled with this, d upon n would be cancelled with this, because they are, when they are being multiplied, d would be cancelled with d and this length would be cancelled with this. So we can write it f is equal to function of Reynolds number and epsilon upon d. So now, it means that if we want to calculate the friction factor for the turbulent flow, then because for the laminar flow, it was only a function of Reynolds number, it was 64 upon Reynolds number, if you remember in the beginning of today's lecture. But for the turbulent flow, we also need to include the roughness element. Roughness, so why is that? Why we need roughness to be considered for the turbulent flow? Because for the turbulent flow in the near wall region, the velocity is very. For the laminar flow, why don't we consider the reference element? Because that in the laminar region, the near wall velocity is very low. So even if there is some roughness element, the velocity is already very low, so it is not very much disturbed by the presence of that roughness element. But for the turbulent flow, because the near wall velocity is very high due to that rapid mixing of fluid, so that's why that high velocity is disturbed quite significantly by the presence of these surface roughness. So they have shown the that very that zoomed in view. So for the turbulent flow, we can see that because the velocity is very high, so roughness element becomes very significant. But for the laminar flow, because that velocity would be achieved after some distance from the wall here. So for that case, the roughness element for the laminar flow doesn't play any critical part. So for that reason, we do not include it for the calculation of friction factor in the laminar flow, because there is one thing I can write it here. That is the last thing. There is a layer. Okay, there is a layer in the near wall region. This distance, which is called viscous sublayer. In viscous sublayer, the velocity, the viscosity effect is very high, is high. For the laminar flow, viscous layer is very large as compared to turbulent flow, because in the turbulent flow, viscous layer shrinks near the wall because the inertial effects are more. Flow momentum is more, so that's why the viscous layer becomes very near to the wall. So that's why for the turbulent flow, when it comes very near to the wall, the surface toughness element becomes very important. So I hope that you got the crux of it. I won't take much longer. So if there is any question, you can ask.